Hi, this is Mrs. Roble. This is Chapter 13, Gases, Part 2. So in the previous video, we looked at gases, their behaviors with Avogadro's hypothesis, Boyle's law, and Charles' law. So today we're going to look at another law, which is called GAY-LUSSAC'S law. So this Frenchman came up with a relationship where the pressure that is exerted by a gas, notice that it's proportional to temperature. And you're ignoring volume and the number of moles. So when you represent it with the variables, notice that it's pressure divided by temperature, and that's equal to a constant. And you can relate two different gases or two different situations here with P1 over T1 equals P2 over T2. So if you know three of the variables, you can solve for the fourth variable. The question is, if we're looking at 0 Kelvin, what does that mean about molecular motion or kinetic energy? We'll talk more about this in class. Okay, so another law that we look at is what we call combined gas law. So we can take Boyle's law, Charles' law, and GAY-Lussac'S law and combine them together into one equation. Now notice that we are ignoring the amount of moles. They are essentially the same. They do not change. And together these three gas laws we call the combined gas law. So when you write the combined gas law, notice it's P1 times V1 over T1. And if you know about 5 of the variables, you can solve for the last unknown variable. Now this chart gives you a good representation of the different gas laws that you've learned up to this point. So notice Boyle's law, you're essentially multiplying pressure times volume, whereas Charles' law, you're taking volume divided by temperature. Gay-Lussac, you're taking pressure divided by temperature. And then lastly, you have combined, which is pressure times volume over temperature. So you might want to make flashcards so you know all the different gas laws, because these will not be given to you on a quiz or a test. Okay, so the last law we're going to look at is ideal gas law. And notice that we're looking at everything. So we're looking at the amount in moles, we're looking at temperature, we're looking at volume, pressure. So we're not assuming anything is constant. Now, if we took Charles' law and we rewrote it a different way, we'd say volume equals a constant times temperature. And then if we took pressure divided by moles equal to a constant and we rewrote it, we could represent it a different way, saying that pressure equals a constant times moles. Now, if we combine these two equations together and we multiply them out, notice it would be pressure times volume times two constants times monomoles and temperature. Chemists decided that they could take these two constants and convert them into what we call R, or the ideal gas law constant. The final equation that you're left with is what we call Pivnert. So this is how I remember it. PV equals nRT. And you will always be given R. This is not something that you have to memorize. In your book, they show you the different R values, and the one thing that you have to pay attention to is the pressure. So depending on what the pressure is, that is going to determine the type of R that you have. So you always want to look at your units to make sure you're using the right R value, because I've had students that supplied the wrong R value and got the problem incorrect because of it. Okay, so the last thing we're going to talk about is density. And from previous experience, you know that density is mass divided by volume. We can rewrite it another way. And big M, by the way, is molar mass. So this is molar mass. Don't confuse it with lowercase m, which would be just mass. Okay. So D times V equals molar mass. And we're going to do problems where if we know the molar mass, we can determine the density of the gas. Okay, so D times V equals molar mass. And if the volume has a constant, please note that mass does not change. So we could set it up where we're looking at two different states. We have density 1 times volume 1 equals molar mass, which can be said to be equal density of the second state times volume 2. Please note that volume and density are inversely related. So if density increases, volume has to decrease. Okay, we actually find the opposite that happens with pressure. So notice that density and pressure are directly related. So if you increase pressure, you have to see an increase in density. And please note that density and temperature are different. They're actually inversely related. So if temperature decreases, density would increase. Okay, now we can also take the combined gas law and we could rewrite it where V1 equals molar mass over density 1, and we could say that volume 2 is molar mass divided by density 2. By doing that, we substitute it for V, and we find that we would get a final equation here, which is pressure divided by D1 times T1 equals pressure 2 divided by density 2 times T2. So obviously if we have 5 of the variables and we're missing one, we can solve for that missing variable. And we will practice these type of problems in class.